Hi there, this is Jude Socrates. Welcome to video number 36 for my series on multivariable calculus, which is known as Math 5C at Pasadena University College. So today we're going to talk about the divergence and the curl of a vector field. And we're going to see a symbol that we saw a few videos ago when we constructed the gradient of the scalar function in three variables. So I will see you on page 340. Alright, so this is how we constructed the gradient of scalar function. This was the symbol, that's the NAMBLA symbol with an arrow on top. So basically we just take the three partial derivatives of our function and we put them together into a vector. Okay? So we said that if a vector field has this form, then it's what we call a conservative field, and our function f is called a potential for that field. Okay, so quick review. Here's a very simple scalar function. Okay, partial with respect to x, we get 15x squared, y squared is equal to 4. Partial with respect to y, we're going to get 10x cubed, y is equal to 4. Yep. Partial with respect to z, we're going to get 20x cubed, y squared, z cubed. Excellent. So that is the gradient of our scalar function. So it's almost like it's a function. Okay, the gradient symbol is a function. The input, though, is a function, and the output is a vector field. Okay? So because the input is a function, mathematicians have a fancier term for it. We call it an operator. Okay, so an operator that you've already seen since a couple of semesters ago is the derivative operator. Okay, think of it as a function that changes a function. Okay, so we know that the derivative of the sine function is the cosine function. So the input to the derivative operator is sine. The output is cosine. Okay, if you input e to the x, the output will also be e to the x. If you input ln of x, the output is 1 over x. Okay? So it's a lot like a function, except again, instead of calling it a function, we call it an operator. Alright, so we use the letter capital D for the derivative. So in the same way, we are going to use the gradient symbol to construct what's called the del operator. Okay? So imagine that we have these three partial derivatives. And it almost looks like there's a common factor of f, and we factor that out. Okay, of course, that is complete nonsense. That is not what we're doing. Okay? So, think of this vector now as an operation. Okay? And it's going to be called the del operator. And by itself, okay, that's just kind of sitting there doing nothing. Okay? But as soon as we put a function beside it, then it can do something. Okay? So just like the capital D symbol for derivative, it doesn't mean anything. Okay? It just means I'm waiting for you to give me a function and I'm going to give you the derivative. Okay? So it's the same thing over here. The del operator is waiting for a function in three variables, and as soon as you put it beside the del operator, then it's going to give you the gradient of your scalar function. Alright, so now we're going to upgrade what the del operator does. Instead of feeding it a scalar function, we're going to feed it a vector field. Okay? So we have f, a function with p, q, and r as its components, and let's assume that they're all differentiable. So you can get partial x, partial y, partial z of all three components. Okay? So we are going to create the divergence of f, and the output will be a scalar function. Okay? We're going to use the dot product. We have the del operator, and we're going to dot it with our vector field. Okay? So we're going to get the partial of p with respect to x, plus the partial of q with respect to y, plus the partial of r with respect to z. Okay? So each of these is a scalar function. We're going to add them all together. That's the divergence of our vector field f. Okay? So similarly, we are going to construct the curl of f. So this time, instead of the dot product, we're going to use a cross product. Okay. So if you remember from chapter 1, okay, that's a more complicated operation. And an easy way to remember it is using the 3 by 3 determinant. Okay. So what we're going to do is we're going to put I, j, and k on the top row. We're going to put the partial derivative symbols on the second row. And then we're going to put our components in the third row. Okay. So remember how to compute the 3 by 3 determinant. Okay, so don't worry, of course, we'll do examples. Okay, who goes with I? First component. Okay, you're going to take partial with respect to y of r minus partial with respect to z of q. Okay, so remember, you're going to make a little cross over here. Okay, so that is what's going to go into the first component of the cross product. Okay, second component is tricky. Okay, instead of going left to right, the correct way to do j is right to left first. So partial with respect to z of p minus partial with respect to x of r. Okay, that's right over there. Okay. So for k, you go back to left to right first. So we have partial with respect to x of q minus partial with respect to y of p. Okay, so let's go to our workroom and let's work out. Okay, so here is a vector field, and not putting it in the vector notation because we're going to make Scientific Notebook find the correct answer for us after we found our answer. Okay, so let's find the divergence. We're going to take partial of x of this, partial of y of this, and partial of z of this. Okay, so from the top, so let's see, partial with respect to x, we're going to get, let's like this, 6x squared, and then x goes away, that becomes 7z. There's no x there, so that's it for p. Partial of q with respect to y. Okay, so let's see, y there, so we need 5xz. There's y there, so that's a minus 3x. Z squared goes away. There's no y over there. Last term. Take the partial of this with respect to z. You know what? They're all single z. So let's make it a little bit fancier. So how about z to the 4th power? Haha. Okay, so we get 4x squared plus 9xy squared, and then plus 24yz. Okay, so there you go. That's our divergence. Oh, great Scientific Notebook. Did we get it right? Divergence. So we get, oh, check it out. Yes, 6x squared with a 4x squared. So yes, that does simplify into 10x squared. Okay, so that can go away. Anything else we can put together? I think that's it. 9xy squared, correct. 5xz, correct. Minus 3x, correct. 24yz cubed, there it is, and 7z. Okay, so that is the divergence of our. Alright, so the curl is fancier. Okay, we're going to do our 3 by 3 determinant. Okay, so copy over here, and we're going to put our components down at the bottom row. This, and this, and this. Okay, so there are a lot more, lots more derivatives that we are going to have to compute. That's coming up next. Okay, so let's create a blank vector. Okay. For I, partial with respect to y of this. There's no y there. I see a y there. So I'm going to do this. I'll copy that, and 9 becomes 18. X stays y. Oh, there's another y there, so we're going to get 6z to the 4. Okay, there you go. And then backwards, partial with respect to z, that's going to have a minus sign. Okay, so, oh cool, there's a 5xy there. That was 0, and then 2. Okay, anything simplifies? I don't think so. Right, J. Remember, right to left first. Partial with respect to z of this. Oh, how nice. Only one term survives. That's only one with a z. And then partial with respect to x of this. So minus, I see 8xz plus 9, and the x goes away, and there is no x over here. Okay, so that's about it for J. Nothing simple. K, back to left to right. So x is in 2 terms. I will copy these 2 terms. The derivative is 8xz, and x goes over there. Okay. And, oh, I'm sorry. Was I in the right place? No. Wrong. And you're going, what's he doing? For k, back here, left to right. So 5xyz, so these two have x's. So we have 5yz minus 3y. Okay. And then minus the other direction. So minus partial with respect to y of this. There's no y there, no y there. Oh, how convenient. So that's just a 12y. And it looks like that becomes minus 15y. Okay? So let us check. Oh, wise and all-knowing scientific notebook. Vector calculus curve. Let's see. 6z to the 4th minus 5xy minus 2z plus 18xyz. Excellent. 7x minus 8xz minus 9y squared. Yep. And then 5yz minus 15y. Yep, it does simplify. Okay, so those are our divergence and the curl. Okay, so just to recap, divergence is a scalar function. Okay, it's not a vector, it's a scalar, it's a dot product. But the curl is a vector field. Alright, so here's our second example. We want the curl of the gradient of f. Okay, so does that make sense? The gradient of f, we make the vector with a partial derivative, so that's a vector field. And then we can take its curl. Okay, so that makes perfect sense. Can you take the gradient of the curl of f? No, that doesn't make sense because gradient needs a scalar function as an input. Okay, and curl of a scalar doesn't even make any sense at all. Okay, so forget about it. Order of operations matter. Okay, so that's our gradient symbol, and we will just take the partial derivatives of this function, and we will assemble them into a vector. Okay. Alright, so here's our blank vector. First, take the partial derivative with respect to x. So we get 10x plus 6y, and then there's no x there, plus 4yz. Okay. Start over. Take the partial derivative with respect to y. So we get 6x plus 6y z, and then plus 4x z. Yeah. And then partial with respect to z. So 0, 0, 3y squared, and 4xy. Okay, are we correct? Compute vector calculus gradient. What's our grade for our gradient? Looks like we get an A+. Yes, everything is correct. Excellent. So now what we're going to do is we're going to find the curl of the gradient. Okay, so this is our answer from our previous example. I'm just going to take this and match it. Yeah. Haha, that's our new vector field. Okay, so we are going to assemble a curl. Partial with respect to y of this. So we get 6y plus 4x minus. Backwards, partial with respect to z, we get 6y and minus 4. Oh, what's happening here? Ooh, maybe I made a mistake. Let's see. For j, we go right to left first. Partial with respect to z. 0, 0, 4y. Yeah. And then minus partial with respect to x of this. 0, oh wait, what? 4y? Oh, what is happening? Now for k. Partial with respect of this. You get 6 and 4z, and then we subtract partial y. Wait a minute. 6, that's going to count. What's going to get left behind? Oh no. Oh no. Plus 4z. Nothing is going to get left behind. Everything is going to become 0. Why? What happened? Because I did something stupid. That should be plus 4x. Yeah. Double dipping. Minus, minus, no. Just 1 minus. There you go. All zeros. Okay? So that is not an accident. Okay? Turns out that if you get a curl of the gradient of any function, any scalar function, as long as it's differentiable, okay? And furthermore, wait a minute. Let's think about this. Wasn't this made of partial derivatives, right? And then we're getting another partial derivative. I hope that reminds you of something that you did in basic calculus, where you had the derivative and you took a second derivative. So therefore, these, when you take a partial derivative of partial derivatives, yes, you get what are called second order partial derivatives. And in this case, they're going to cancel out each other. Alright, so let's start with a scalar function, and then we can take first partial derivative with respect to x, or first partial derivative with respect to y. Okay? So let's just keep it to 2 variables for now, right? So if that is again a differentiable function in x, then you can take another partial derivative with respect to x. So that is called the second order partial derivative with respect to x squared. Okay? So notice in the subscript notation we have fxx, and in the del notation we have del squared f with respect to del x squared. Okay, so it's a little bit weird. Why is the square there and not after the f? Okay, well, part of it is because if you put it above the f, you might think, oh, you're going to square f first, which does not make sense, of course. Okay, so yeah, let's go down here. Same thing if you have partial f with respect to y, and then you take another derivative with respect to y. You get a symbol very, very similar to what we have up here. Okay? It gets interesting when you take a partial of f with respect to x, and then with respect to y, a different variable. Okay? So that is written as f sub xy. Okay, so notice that y is to the left of x. And when you turn it into the del notation, y stays to the left of x, okay, because we have those del symbols, okay? But in the subscript notation, it's f sub xy, okay? What's the logic behind these symbols? Okay, there's a logic, okay? When you read this, you read partial of f first with respect to x, then with respect to y, okay? When you read this, you take partial squared f with respect to x first, and then with respect to y. Okay? It's almost like you're going to the right first, then you go down back to the left. Because your eye will go left to right, down, right to left. Okay? Instead of left to right and then down to the left, left, right. No, no, no. You kind of make a U. Okay? So partial squared f with respect to x and then with respect to y. Okay? This next symbol is, of course, the reverse of this next partial derivative. Okay? You take first the partial of f with respect to y, and then with respect to x. Okay? So that is written as fyx, and partial squared f with respect to y, and then with respect to x. Okay? They do not mean the same thing. Okay, think about it. First you take the partial with respect to x, and then with respect to y. Okay? This is backwards. Take the partial with respect to y, and then with respect to x. Okay? And in mathematics, we keep telling you the order of operation matters. Okay? None of those stupid memes on social media. Oh, PEMDAS. Don't forget your PEMDAS. Like, who cares? Well, of course we care. As mathematicians, we care. So these two symbols definitely don't mean the same. Okay, so the same thing, of course, can be said about functions in free variables. Okay, except there are a lot more mixed partial derivatives. Okay, so here's a simple function in free variable. We know how to take the partial with respect to x, y, and z. So that's just 14x, blah, blah, blah. And then for y, we get 21y squared, blah, blah, blah. Partial z, 35, blah, 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 z to the 4. Okay? So now, let's find the second order partial derivatives of the first partial derivative with respect to all three variables, x, y, and z. Okay? So we're going to focus our attention on this, and we're going to take its three partial derivatives. Okay? Forget about this. Focus on this. Okay. So with respect to x, we get 14 by cubed fifths. With respect to y, 14 times 6, 42, x, y squared fifth. With respect to z, 14 times 5, you get 70, and so on. You know what to do. Okay. So those are the three partial derivatives of the first partial derivative of f with respect to x. Okay. So now you can repeat the process for y and z. Okay, partial y, partial z. And you get this list. We're looking at now at all the 3 times 3, 9 second order partial derivatives. Okay? So again, the mixed partial derivatives, they don't mean the same thing. But you're not blind. Check out fxy. Where's fyx? Oh, there you are. Oh, wow, it's exactly the same. How about fxz? Where is fzx? There you are. Ooh, they're exactly the same. So what is missing? Here's fyz, and here is fzy. They are exactly the same. Okay? So of course, there are no coincidences in mathematics. There is a reason why they are the same in this case. Alright, so does it happen all the time? Not quite. Okay? There is a condition you have to fulfill. Suppose that f is a function so that all second order partial derivatives exist and they are continuous. Then fxy equals fyx, fxz equals fzx, and fyz equals fzy. Okay? And of course, the first equation is true for a function in just two variables. Okay? This condition on continuity actually matters. Okay? And you might say, but we haven't really talked about continuity, have we? Perfectly fair. Okay? I do continuity at the very last chapter of this book. Okay? My goal is to basically give you an instinct, a somewhat pedestrian understanding for continuity, differentiability, partial derivatives, and then we dig deeper at the last chapter. Okay? So, when I was doing my research on this, I found, oh, wait a minute, okay, I want to prove Clairaut's theorem. And there is an amazing, clever proof for Clairaut's theorem that uses Fubini's theorem. Okay, you remember Fubini? Fubini said that it doesn't matter if you compute the double integral over a rectangle with respect to x first and then with respect to y, or with respect to y squared and then with respect to x. Okay, as long as what you are integrating is continuous. Okay, continuity matters for Fubini's theorem as well, although, of course, we did not prove Fubini's theorem. Okay, so if both, okay, so let's do it for just fxy, and of course, similar argument works for if you want fyz, fzy, then you're going to make a double integral with respect to those two functions. Okay, so fxy and fyx are both continuous. So if you take the difference, that is another continuous function. Okay, so we want to show if they're the same, then this has to be 0 all the time. Okay, at every point on our rectangle. Okay, so by continuity, Fubini's theorem says that we can compute a double integral of g of xy, and it doesn't matter if we have dx inside or dy inside. Okay, so we can write this double integral in two pieces. Okay, and let's remember what they mean. Okay, so let me keep scrolling so that I'm out of the way here. Now I'm out of the way. Okay, so what is the meaning of fxy? You take the partial derivative first of x and with respect to x, and then with respect to y. What does fyx mean? First you take partial with respect to y, then with respect to x. Okay? But we're integrating both of these over the same rectangle. Okay, that's the key. So with the same rectangle. So because the outer derivative, partial derivative with respect to y, let's integrate first with respect to dy. Okay? Because we know that this antiderivative is just partial of f with respect to x. Okay? You take the partial y, then integrate dy, you're back where you started. Okay? Similarly here, because the outer partial is with respect to x, let's do dx inside, dy outside. Did I tell you it's clever? It's really clever. Okay, so we know how to find the antiderivative there. We plug in d, we plug in c, and subtract. Here we plug in b, we plug in a, we subtract. Okay, so we are down to partial of f with respect to x. We plug in d, so partial x fxd, minus partial f with respect to x, fxc. Okay? Similarly, here it's the x's that we plug in. So we have partial y f dy minus partial y f ay. Okay, that's what we have over there. Okay, but wait, there's more. These are again partial derivatives with respect to the correct dx. Okay, so again, the antiderivative of this partial derivative is fxd, and the antiderivative of this partial derivative is fxc. It's hilarious. I was reading this like, oh my god, it's almost like witchcraft. Okay, so similarly here, we'll get fdy minus fay. Okay, plug in the endpoints. So here, x from a to b, so fbd minus, okay. So I think that should be I'm sorry. Okay. Hang on. I'm not reading the whole thing. So I'm taking this whole thing and going from a to b. Okay. So fbd minus fbc, and then plug in a. Okay. So minus fad minus fac. Whew. Okay. That works out. Now, minus this thing. Okay, so notice the double brackets here. Okay, so at B, you have FBD minus FAD. correct so far. Minus, plug in C, FBC minus FAC. Woo, that works out. Okay, and guess what? That FBD cancels with this minus FBD. That minus FBC cancels with this plus. There's a plus there, FBC. Minus FAD cancels with plus FAD. Plus FAC cancels with minus, minus, minus. Three minuses, minus FAC. Okay, so exactly all four terms, 1, 2, 3, 4, 5, 7, 8 terms, 4 pairs, cancel each other perfectly to get 0. Okay, we're not yet done though. You might say, oh, that's nice, that's nice. The double integral of g over r is always 0, okay, over that entire rectangle. Okay, but wait a minute. Okay, our domain is a to b, c to d. Okay, our function is defined over that entire rectangle. Okay, but what if we just restrict our function to a smaller rectangle inside that rectangle? Okay, call it a prime, b prime, c prime, d prime. Any difference in these computations? A prime to b prime to just put a prime everywhere. Still works, right? You are still going to get 0 on every itty-bitty sub-rectangle that we see inside our big rectangle. Okay? So, what's our main goal? What are we trying to show again? We want to show that this function on two variables is 0 at every point in that rectangle. What we have so far is that if you integrate that function over every rectangle, no matter how small or how big, as long as you're inside that main rectangle, that double integral will be 0. Okay. So now, we're going to use continuity one more time. Okay? This function g is continuous. Alright? And again, my apologies, but we haven't really dug into the meaning of continuity. Okay? So, what if your function is not 0 all the time? Okay? So, 0 means you're on the xy plane. Right? So, if you're not 0, then you're either above the xy plane or below the xy plane. Okay? So, let's assume you're above the xy plane. Okay? So, let's exaggerate. Let's say you're 1 unit above the xy plane. Okay? Continuity means when you get close to this point where it's not 0, you need to be close to this z value. Okay, but that z value is 1 unit from the origin, from 0. Okay, so there will come a point that if you're near that point, you should be close to this point, so you're somewhere up there. Okay, the graph of your function is somewhere up there. Okay, so let me show you a picture. Okay, so there it is. Okay, I have a point somewhere inside our domain where the function is positive. Okay, so therefore, somewhere close to that point, it will stay positive. Okay, it's not going to be 0, it's not going to be negative. Okay, let's go back to chapter 2. Remember diagrams that look like this? Okay, if your function is always positive, can the double integral be 0? No, of course not. Okay? Because that double integral represents a volume. Okay? So therefore, this cannot happen. It's not possible that your function is positive somewhere inside that rectangle. Otherwise, you'll get a double integral over a smaller rectangle, which will be positive. Okay? And of course, a similar reasoning works if your function suddenly becomes negative. No, that is not going to happen. Okay? So therefore, your function has to be 0 everywhere on that rectangle. The two mixed partial derivatives have to be exactly the same. Okay, so there you go. That is exactly what we need to show that if you have scalar function where the second order partial derivatives all exist and are continuous, then the curl of that gradient function has to be the 0 vector. Okay, so yeah, it's basically just how to implement the curl. Okay, so remember, you take the cross product of the del operator with the partials, fx, fy, fc. Remember, we put them at the bottom. Okay, so what do we get? Partial of z with respect to y, partial of fz with respect to y, minus partial of fy with respect to z. Ooh, that's fzy minus fyz, 0. Okay, same thing for j, fxz minus fdx, that's 0. For k, fyx minus fxy, that is going to be 0 all over for any point on your domain. Okay, so those partial derivatives cancel out. The curl is the 0 vector. Okay, unfortunately, the converse of this is not true in general. Okay, but there is a nice partial converse, and it works for vector fields which are defined everywhere. Okay, so if someone gave you a vector field so that when you computed the curl of that vector field, you got the 0 vector, and that field is defined everywhere, okay, then that function has to be conservative. Okay? So remember though, when we did the fundamental theorem for contour integrals, and that is where we encountered conservative fields, we said, okay, if you believe that this is a conservative field, try to look for a potential. Okay? So here, you don't have to believe anymore. Okay, you can actually check that your field is conservative. Right? If the curl is not 0, then don't bother wasting your time. Your field is not going to be conservative. You will not be able to find a potential function. Alright, so now let's talk about what exactly is the meaning of the divergence and the curl of a vector field. Okay, we're going to start with the curl. Okay, so the conclusion that we're going to get here, the main point, is that curl represents a rotation. Okay, so if you imagine that your vector field is a river, okay, and you toss, let's say, a ping pong ball into that river, the ball is going to spin, okay, and as it moves along the river, it's going to spin along different axes, okay. So the axis of the spin tells you the direction of the curl vector, okay, and how fast the ball is spinning tells you the magnitude of the curl. Okay, so the faster it's spinning, the larger the magnitude of your curl. Okay, that's great, but wait a minute. Curl is about partial derivatives, right? We have ry minus q0 with all these awful partial derivatives. I mean, what does this have to do with spinning? Okay, so I have a Rubik's Cube here to demonstrate the principle. Okay, so imagine that you're pushing a box along the floor. Okay, so you're moving, let's say, in the x direction. Okay, and well, if your left hand and right hand are left arm and right arm are equally strong, then of course the box will just slide forward. Okay, but what if, let's say most people are right-handed, your right arm is stronger than your left, so it's going to spin like this as you push along. Okay, I'm left-handed, so if my left arm, yes, my left arm is stronger than my right arm, then it's going to spin like this. Oh, that's your hunt. Okay, back to this. What a bad dog. So if you're pushing and your left or right arm are not balanced, then it's going to spin like this. Check it out. We're spinning, according to the right-hand rule, we're spinning with an axis towards the z-axis. Okay, is that the only way that it can roll around the z-axis? Well, if you're pushing this way, okay, instead of towards the x, you push towards the y. Okay? Then, if your right arm is stronger than your left, then it's going to spin this way as well. So it's going to go like this. Okay? But if your left is stronger than your right, then it's going to spin like this. Okay? So, yeah, we said that the direction of the spin, okay, is the direction of the curve. Okay? So notice that if it's spinning like this, your right hand rule comes up. But if you're spinning in the opposite direction, your right hand rule thumbs down. Okay? So let's see what this has to do now with our partial. Okay, so curl is ry minus qz, pz minus rx, qx minus ty. Okay, so let's talk about the middle component. Okay, we can talk about any of the three. Let's just focus on the middle component, pz minus rx. Okay, let's assume that both of them are positive. Okay, pz is positive, rx is positive. Okay, what does it mean for a derivative to be positive? Your function is increasing. Okay, so therefore, p is increasing and r is also increasing. Okay, but remember, p, q, and r go along the axis. So p is going along x towards you, q is going along y to your right, and r is going up towards z. Okay, so let's pretend that, in the same way we do a triple integral, we subdivide a brick into small sub-blocks, sub-bricks, okay? So remember that we have these partitions, okay? So as before, we have delta x, delta y, and delta z, okay? So let's see what's going to happen to our brick, our sub-brick, as we push using p, q, and r. Okay, so we are looking at the j component of the curve. J component is along the y-axis. Okay, so I'm sorry, yeah, the y-axis is over here. That's the x-axis, and this is the y-axis. Okay, so here's j, and here's j. Okay, p is pointing towards the x-axis, the positive x-axis. But partial of p with respect to z is positive. That means that p is increasing in which direction though? Along the z-axis. So as you go up along z, your p will increase. Okay? So imagine now you're pushing with two hands, one on top of the brick, the other at the bottom. Okay? So if your upper hand is pushing stronger with more force than your lower hand, then it's going to roll forward, okay? And that's what we call a torque, okay? The net difference of these two multiplied by the distance between them, that is the torque produced by P. It's a rotation, a spin, okay? So according to our right-hand rule, because your P above is greater than your P below, you're spinning around the positive y-axis. Okay? Let's think about R now. PQR. R is pointing towards the z-axis. Okay? And let's say that, which partial do we want? Where is the R? There it is, Rx. Partial of R with respect to x is positive. Okay? So therefore, as we move along the x-axis, positive x-axis, your R will increase. Okay, so this time, you're pushing from the bottom of the brick. Okay, imagine you're pushing along the bottom of the brick. Okay, so your left hand is stronger than the right hand. Okay, how far apart are they separated? By delta x. Okay, so the torque that is going to produce now is the difference between these two times the distance between them, delta x. Okay, and notice this time it's spinning in the opposite direction. Ooh. So that's along the negative y-axis. Okay, so there we go. The torque that we produce, okay, for T is the difference of the two at the two endpoints multiplied by the distance between them. But let's pretend we're dividing and multiplying by another delta z. That looks now like a partial derivative, doesn't it? It's approximately partial q with respect to z, and we get delta z squared. So similarly for r, the torque it produces is in the opposite direction, because we assume that r is also positive. Rx is also positive. Okay? So now you take the difference between the forward and the backwards, okay, multiplied by the distance between them, which is delta x, and then we fix it by multiplying and dividing by another delta x. Okay, so now we have an opposite, minus rx times delta x squared. Okay, so I showed you a Rubik's Cube. Okay, that's a delta z squared, that's a delta x squared. Okay, so if we pretend that the brick is actually a cube, okay, delta x, delta y, delta z, they're all the same. So therefore, when you add the contribution of those two torques, you just get the difference, approximately, of tz minus rx times the side of the cube squared. Okay, so that is why, if you put them all together, okay, the torque that you get, the net torque that you get, is approximately the curl of the field times the area, essentially, of one side of your cube. Alright, so that is curl. It's about spin. What about divergence? Okay, so surprisingly, it has to do with a flux integral. Okay, and again, imagine that you have a sub-brick, but this time, we don't need to have the sides of the brick to be exactly the same dimension, if I'm not mistaken. So, what is the flux of our vector field going across the 6 surfaces, the 6 sides that make up this cube? Okay, so again, P is going in the x direction. Okay, so it's only going to flow through the front and the back of your cube. Okay, it's not going to go through the left and right side or through the top and bottom. Okay, it's perpendicular to those two. Remember, we have to fix an orientation. The normal vectors are perpendicular to the cube. Okay, so in this case, okay, let's make them point here. Okay, we're going to enter the cube through the back and exit to the front. Okay, but at the back, the outward normal vector is pointing towards the negative x-axis. It's negative I. Okay, when you exit the cube through the front, the normal vector is pointing towards positive x-axis. Okay, and what did we say is the flux? Okay, it's the product of the vector field with the area, and the sign tells you if it's a positive or a negative contribution. Okay, similarly along the y-axis, okay, Q will enter on the left, where the outward normal is towards negative j, and exit on the right, where the outward normal is along positive j. Okay, and similarly along from the bottom face and the top face of your grid. Okay, so let's compute the total flux that we're going to get. For the front and the back, it's just the field times the area, which is delta y delta z. Okay, but in the front, you're going in the positive x direction. In the back, you're going in the negative, going against I. Okay, so therefore you're subtracting. We've seen this before. Fix it by dividing by delta x, multiplying by delta x. Oh, wait a minute. Delta x, delta y, delta z. That's now a delta v. Okay. So same thing with the q contribution. Okay. We're going to get a partial here, a partial q with respect to x. Here we get a partial q with respect to y. Sounds familiar. We're getting the divergence. Okay. So similarly for the top and the bottom, it's going to be partial of r with respect to z. That makes the contribution times delta v. Okay. So therefore, when you add it all together and you take the limit as delta v gets smaller and smaller, then the total flux that you get becomes exact. Okay. So we can write it as the limit as delta v goes to 0 of the flux of your field across this little brick of size delta x, delta y, delta z is going to be the divergence of F at one of the corners of your brick. Oh wow, looks like this is one of my longest videos. I hope you know how to use your pause button, right? Okay, so to end our video, we're going to talk about how divergence and curl are related to Green's theorem. Okay? You probably noticed that in curl, we saw qx minus py in the computation for the curl of that. Okay? Green's theorem, though, is only about a vector field in 2 dimensions, on the plane only. Okay? So to extend it to 3 dimensions, easiest way is to just put 0 for our z component. Okay? P and Q don't depend on z either. Okay, so essentially that's a vector field that depends only on x and y. Okay, so what's the curl of this? We're going to get 0 and partial with respect to z of q. Well, there is no z in q, so that's going to be 0. Okay, how about for shape partial with respect to z of p? Again, there's no z in p, so that's 0 minus 0. Good, 0. Now, for k, partial of q with respect to x minus partial of q with respect to y. Qx minus qy. Same as the general formula. Okay? So, therefore, that is what appears in Green's theorem. Qx minus qy. Remember? Okay, for the divergence, though, we don't get qx minus qy. Okay, we get something else. So we need partial of q with respect to x plus partial of q with respect to y, partial of who cares at 0 with respect to z. So we only get px plus qy. Okay, so we don't get qx minus py. Okay, so one way to rewrite, therefore, this equation from Green's theorem is to extract qx minus py from the curl of our field. Okay? But wait a minute. How do you get the z component of a vector? You dot it with k. Right? That's the easiest, sneakiest way you can extract the z coordinate of a vector. Okay, so therefore, we can write Green's theorem, the equation that we get from Green's theorem, definitely in this way. Okay, there's our qx minus py. When you dot that, when you dot the curl with k, you get qx minus py. Okay. What about this guy? I have divergence over here, and that's px plus qy. Wait a minute, something's fishy over there. But wait a minute, the left side is not the same. Okay? There's an n here. What the hell is that? F dot n ds. That, we were just talking about flux integrals a few minutes ago, right? That looks like something out of a flux integral, doesn't it? Right? Except this is a capital letter S for a flux integral. Okay? So, comments, this is the last part. Let's see what that symbol means. Okay, so unit outward net vector to a solid. Okay, we know more or less what that means. Okay, you take a surface, okay, and then you create the normal vectors by taking some kind of cross product, okay, and then you turn it into a unit normal vector, okay. So what we're going to do is we're going to create something analogous to a parametric curve on the xy plane, okay. And I do have a picture down here, so just wait a second, okay. How are we going to create these normal vectors, these unit normal vectors? We're going to start with a tangent vector. Okay, so we now have to take the derivative of a parametric curve, and if the derivative is never 0, we can create a unit vector. Okay, so this will appear in chapter 7. Okay, we have capital T, the unit tangent vector. Take the tangent vector, divide by its length. Okay, so how are we going to create a unit normal vector? Okay, so normal means perpendicular. Okay? So here's the idea. If your curve is being traced, let's say in a counterclockwise way, which is what we usually do, your tangent vector, your unit tangent vector is going to look like this. Okay? I want a unit vector that's pointing away from the domain. Okay, away from the region. So kind of like our normal vectors on a surface. Okay? This time they're pointing away from the solid, which is bounded by the surface. Okay? Alright, so how are we going to do that? Well, think about perpendicularity. Okay? I need a vector that when you dot it with t, you're going to get 0. T is over here. Okay? So, if I exchange these two, I get y prime here, x prime here, and then I multiply them. Aha! They're both going to be x prime, y prime, x prime. Okay? One of them has to be negative though, because we're going to add them together and make dot product. Okay? So, where are we going to put the negative sign? Okay? The negative sign will go on the right, the y coordinate, the new y coordinate. Okay? So, why is that? Well, it's because I had to take a drink of water. As I said, it's because, okay, let's take this tangent vector over here. Okay, that's a unit tangent vector. I'm picking this because you have a positive x coordinate and a positive y coordinate. Okay? I want to be rotated clockwise from P so that I'm pointing away from the domain. Okay? So what does that mean? Your x coordinate has to stay positive, but your y coordinate now has to become negative. Okay? So that is why you put negative on the new y coordinate. When you got them together, you're going to get 0. Okay, so now we're ready to compute the left side of this equation. Hopefully we'll get the right side. What is the contour integral of f dot n ds? Okay, so let's plug it in. We have f, which is our vector field. Our n is this. And remember that ds is just magnitude of r prime dt. Okay, these cancel, so we just get this vector. We're going to dot it with this vector, dt. Okay, so what does that mean? We're going to multiply this to p, y prime, and then minus q, x prime. Okay, so what we're going to do is we're going to put the minus q in front here because the q goes with the x prime, and x prime dt. Remember, it's dx. Okay? And then we'll have a plus p here, y prime dt. That's dy. Okay? So it's in the order of dx, dy. Okay, so we're almost there. Why is there a minus q here and a plus p over here? Okay, we're used to seeing p dx plus q dy. What's going on here? Not only are they backwards, there's a minus sign there. Okay, can it be any worse? Okay, so to unconfuse ourselves, disconfuse, what's the correct word? Let's use different letters. Okay, we're used to p dx, q dy. Okay, so Green's theorem says contour integral p dx plus q dy is double integral qx minus py. Okay, the p's and q's are confusing us. So let's change them to j and k. Alright? So if we have j dx plus k dy, Green's theorem says we take the k, the q, partial with respect to x. Okay? You take the j, partial with respect to y, and then you subtract. Okay? So this is the model that we're going to use now to proceed from here. Okay? So the minus q corresponds to j, and the p corresponds to the k. Alright? So according to Green's theorem, you start with kx, k is p. So you just have px, okay. And then you have minus jy. Who is the j? J is the minus q. So you have minus q with respect to y. Ta-da! You have px plus qy. That is your divergence because there is no r. Okay? So there you go. That is the second form for Green's theorem, the contour integral of f dot n ds, where n is our unit outward normal vectors, is the double integral of the divergence of f over the domain enclosed by the curve C. Okay? So why are we doing this? Why did we do this? It's because in the next two sections, we are going to finish off this chapter by taking a look at two theorems which look a lot like Green's theorem, except they are three-dimensional analogs. So yes, in the coming sections, that will turn into a flux integral. Double integral over S, f dot n, d capital S. Alright? So yes, that is officially our longest video in our series. Thank you for your patience. Thanks for watching. So until our next video, I hope you enjoy the rest of the day. Bye.